So we are live, yeah. Hi all, good evening. Hope all of you are staying safe and doing good. So welcome to the 44th edition of Geeknight. So for people who are new to this community, to give just an overview of what Geeknight is all about. So Geeknight is a monthly event which is hosted by ThoughtWorks team, and usually this event happens on most of the time it will be happens on third Thursday of every month. And usually this community is to share the latest trends and technologies, best practices, and other interesting things which are evolving in the world of IT industries. And we are this platform can be also used by any of you to present your topics in future event, and we are very well welcoming that and happy to see you all in the future events also to present it. And yeah, so today, right, we are going to discuss on two interesting topics. First one will be like running Spark on Kubernetes, which is going to be presented by Mani, who is a senior consultant in our organization. And next to that, the topic will be like building your own operating system, which will be presented by Ashok. And he is also a senior consultant. And yeah, so this is pretty much an overall agenda of our session today. And if you have any questions, right, at time of the session, please post it in the YouTube chat. We can help you in addressing it then and there. Yeah, that's it pretty much from my side. Over to you, Mani. Yeah, thanks.
Thanks, Rikesh. Welcome everybody to this session. Today's topic of discussion is running Spark on Kubernetes. So I would like to start the session by introducing these two terms, right? Like Spark and Kubernetes. I'm pretty sure many of you are familiar with Spark, but not used Kubernetes. And similarly, there will be other set of folks who have used Kubernetes for deploying their services, but might not have used Spark. For making it beneficial for everybody, we will get into a little bit of overview of what these two tools do on their own, what problem they solve, and how they are going to work together. How can we run Spark jobs on Kubernetes? So that's the whole journey in this particular session. Like Shrikesh pointed out, feel free to put down your questions in the chat then and there. I'll be happy to answer them. Cool. So we have anatomy of a Spark application right here. So, but what is Spark? What is the purpose of a tool like Spark in the space? So Spark is basically a cluster computing tool. And what do we compute here, and why is it so popular? So the mode of computation in Spark is all primarily in memory, and in memory across JVMs. So it's distributed computing in the in memory. So because of this, we get a lot of performance benefits compared to doing computations in a single node. Then there is the scaling problem as well. Like you could only scale vertically, you can't scale horizontally. But with distributed computing, you could scale horizontally with commodity hardware, and depending upon load, you can elasticize the size of your cluster. So how is Spark different from MapReduce jobs that were there before Spark? So Spark came up with this new idea of resilient distributed data set. So when Spark was introduced for the first time, RDD were the primary data structure. And what's so unique about this data structure is that by definition, it's a distributed data set. So if I have, let's say, 100 elements and in an RDD, it's going to be spread across multiple JVMs. It's going to be spread across multiple machines. And it gives a single interface for the programmer to really, work against that data set, just like we work with lists or any other collections. But actually, any other data structure we work with is present in a single machine, single JVM, but this one is going to be spread across multiple. So that's the unique advantage that Spark's data structure offers, and programming with Spark lets us do a lot of transformations in one go, and that makes, because the computation is in memory, that makes the performance of the applications to be super quick. So that's an overview of what Spark does and why it came into purpose in comparison with MapReduce jobs. So what happens underneath? What is an anatomy of a Spark application? So generally, if I want to submit an application, a job to Spark, it goes by Spark submit. So as you can see here, when I do a Spark submit, there is a master node, which is a special node. This particular anatomy is talked with Yarn as a resource manager. So the master node has the Yarn resource manager, and the master node, Spark's master node, is working with multiple worker nodes to get the job done. So the very first thing that the master node does immediately after it receives the Spark submit is to create an application master in the worker node. So that is the second worker node. As we can see here, there is a application master getting created, and in the application master, there will be a driver program that gets created. So this driver program is now going to be responsible for working with the resource manager to negotiate resources. Let's say I need 5 executors now, and I need 2 executors, and so that's the job of a driver program. And it also executes any code that needs to be done in the driver side. Basically, anything that need not be distributed, which can be done in a single node, that's done by the driver. So every worker node will have a node manager. In this case, because of Yarn, we have Yarn node manager. So all of these terminologies actually correspond to their equivalents in Kubernetes world as well. So we'll come to that in a bit. So so that's the breakdown of what components are there and what are their responsibilities when a Spark submit happens. So to summarize, we do a Spark submit to the master node. The master node creates an application master in one of the worker nodes, and the worker node has a driver program which works and negotiates resources. The resources in this case are executors, and it assigns tasks to the executor programs. So this is what Spark does. This is how our program, whatever we have written, gets executed underneath. So driver program also collects the resources or the completion status from executors, and that's when the program exits. Cool. Moving on. So next, let's talk about Kubernetes. So Kubernetes, what is the problem it's solving? Kubernetes is basically it's like in the container world, it lets you easily manage and deploy containers. So Docker containers, if we take a Docker container, and if we want to handle one or two applications, one or two containers, we could handle it ourselves manually. But when we want to, handle a lot of applications at scale, a lot of containers, that's when Kubernetes comes in handy. So Kubernetes has its own complications, but that's mostly in the control plane here. So whenever people choose to use cloud provided services, we will have this dotted line in the control plane taken care by the cloud provider, and hence it becomes really, really easy to really deploy our applications into Kubernetes. So looking at components of Kubernetes, Kubernetes has basically a API server. API server uh, is like an API. Is like the backend API, which interacts with all the nodes, all the Kubernetes nodes running the actual cluster. So it has a backing data store, etcd. This is a key value store that is used by Kubernetes API server. It also has a controller manager. So kube controllers are really interesting in the sense kube controllers can are always in the mode where they have a desired state and there is an actual state. They always try to make the actual state more towards the desired state. So that's the job of Kubernetes controllers. So we also have a scheduler to really schedule the jobs, and we have cron kind of usage that we can have in the control plane using the schedulers. So Kubernetes schedulers are also responsible for scheduling the pods, scheduling containers in the pods, and basically managing the scheduling of pods in which node it should go to. Let's say a request for a new pod has come up, and when a pod is getting created, in which particular node it should come up is taken care by the Kubernetes scheduler. So we have a cloud controller manager. This is more to work with the cloud service providers, how they can integrate and control the control plane. So in each node, Kubernetes runs a kubelet and a kube proxy. So a kubelet is more like the node manager, what we saw here. So it manages the nodes. It is responsible for making sure it creates containers inside the pods, and whatever pods are getting created in this node will communicate with the kubelet, and in turn the kubelet will talk to the API server. So that's about the components in Kubernetes. So in the Spark ecosystem, where does Kubernetes stand? So that's a main question that's coming for us, right? So Spark has a Spark core library. So this Spark core has pretty much the important stuff like the RDD implementations, data sets, and all those things. So there are other libraries built on top of Spark core, like for example, machine learning library. This gives you all the machine learning algorithms implemented, so that when somebody is writing a Spark program, they can use Spark for clustering use cases, classification use cases, and whatnot. Similarly, there is a graphics implementation for graph processing. There is Spark SQL for SQL interface to work with the data frames, and the streaming use case can be solved using the Spark streaming. So this is the interface where Spark programmers primarily interact with. Whereas what is underneath, what happens underneath Spark is what you can see here. So Spark works with one of the resource managers to really negotiate and ask for example, I need so many executors. I need to kill this executor. I need to apply this config to this executor. So those kind of interactions will happen by Spark Core with the resource managers, and that happens to be on Mesos, or there is a built-in standalone scheduler as well with Spark. And this is where Kubernetes comes in as another resource manager for Spark. So currently at the moment, Yarn is most widely used throughout, and Kubernetes is relatively new to this space. And we should also look at this particular integration running Spark on K8s as something that is an experimental feature at the moment. It's not like production ready. It has a lot of gaps that needs to be addressed. There is a community that's heavily working towards this as we speak, but as things stands now, there are a lot of use cases that Spark on Kubernetes doesn't support. And it has come a long way as well. Like around a couple of years back is where the project started, and now there has been a lot of things that the Spark on Kubernetes team has achieved. So it's more on the evolving space, having running Spark on Kubernetes.
Yes, Mani, we have couple of questions here. So So first question is like, what is the difference between Docker and Kubernetes, and in which scenario we should choose Kubernetes over Docker container?
Okay, sure. So Kubernetes is basically your complete container management system, right? So for example, let's take a simple example. Let's say I have a simple accounting app, and all it does is I upload a Excel file, it processes, and it calculates, let's say, everybody's salaries, and it stores that in a database. This is the only application I have in the system. So for this kind of a setup, having you can do it in multiple ways without even taking the container route. But if you're taking the container route, we can just create a Docker container and just execute the Docker container, and that will be enough. As long as the container is up, we'll be able to do our operations with this application. But let's say I have a microservice architecture where I have hundreds of services running, and even in that case, I can have 100 containers and up and running. But what happens if one of the services go down, one of the containers go down for whatever reasons? So in that case, we will probably have to have a lot of manual intervention there. We need to have a sufficient monitoring system to see if all my applications are up and running. If they are not, then if we could have an automated script that detects that this process is down and it could restart it, even then this will not solve the problem, because when one service goes down, based on that, as a ripple effect, other services also might go down. So to completely manage the whole deployment here, Kubernetes comes with as a whole package, so to say. So you can deploy a number of applications, and all you say is, I need this service and have these many replicas. It handles the replicas. When one goes down, it brings up the other. And in the meantime, other services will be handling your requests. Other pods will be handling your requests. So then on top of that, it comes with a lot of authentication and authorization related stuff. Role-based authorization is supported. So otherwise you will have to find some tool which does this for you. So it's like one-stop shop where you have containerized applications, you could get it to the Kubernetes ecosystem, and you reap a lot of benefits out of it in terms of managing the entire suite of applications. So that's the primary advantage, and also it has its own drawbacks because it's trying to solve all the problems. If let's say you don't want to use some built-in role-based authorization, and you want to plug in something else, there's no way to turn off the existing role-based authorization, which means that will also exist. On top of that, you will have to integrate your own authorization system and make that to be used. But you can't make the inbuilt one go away. That's going to stay. So that's there are pros and cons of using Kubernetes. So we should pick this for the right use cases where we have the right demand.
Yes, that answers the question. And one more question, like I think Dharani is using ECS at the right moment to deploy the Spark or to run the Spark job. So his question is like, what value will I get by moving to Kubernetes from ECS?
Okay. So. Okay, I think I'll probably answer this question at the end of the session because there are some drawbacks and limitations of using Spark on Kubernetes, which is going to follow in the coming sessions, in the coming part of the session. So I think I would like to answer that question in the coming place. Is there any other question?
Yeah, one more question, Mani. So, is it ready for production in 3.0 or even earlier releases? Mani, this was the question.
So it's not ready for production yet. In the 2.x series, it's not ready for production. In Spark 3.x, they are trying to, but it's all planned and being worked towards. As things stands now, it's not production ready.
Yeah, thank you.
Cool. Any other questions?
No, Mani, we can carry on.
Okay, cool. So this is where Spark and Kubernetes meet each other. So when a client application does a Spark submit to a Kubernetes cluster, the scheduler and API server are primarily acting to make sure everything works here. So the request is submitted to the Kubernetes cluster, and the first thing that happens in the cluster is a driver pod is created. So the driver Spark driver is nothing but a Kubernetes pod. It's more of a controller pod than really anything else. But it's a pod. When I say a controller pod, why it's supposed to be a controller pod than any other normal pod? Because it's going to manage the executors. Whenever an executor goes down, Spark driver being a controller, it knows the desired state to be 3 executors, and whenever one goes down, it will bring up the executor to make sure we have 3 executors. So that's why it's built as a controller pod. And like once a Spark driver is created, Spark driver is going to start negotiating resources, which are the executors, with the API server, with the Kubernetes master, and it creates these executor instances. So when these executor instances are created, they're going to run and do the computations in the executor nodes, and they will either send the result back to the driver, or they will persist the result and send the status back to the driver, depending on how the program is written. So that's where the program execution happens, and the status is bubbled up back by Spark driver back to the client. So this is the whole workflow, and if we see this is Spark working in cluster mode. Spark can work in both cluster and client mode, and when Spark runs in the cluster mode, the driver program is created in the Kubernetes cluster, whereas if we are running the Spark job in the client mode, in the client's machine, we are going to have the Spark driver program running, and the executors alone will be created in the Kubernetes cluster. Any questions? Cool. So let's see a quick demo of this particular use case. So the workflow is simple. In my machine, I have it's all going to run in my local machine. So I have Minikube, and it's running. So I have a kubelet running, and Minikube is nothing but a single node Kubernetes cluster. So that's running in my machine, and my host is running. I have the API server which is running as well. The API server is running in a particular IP, and the port is 8443. So my Minikube is going to be the Kubernetes cluster, but please note that we have only one node here for the computation. On the other hand, we need to have a program that we have to execute in this particular Kubernetes cluster. So at the moment, I do not have any jobs running. This is the past job that ran before. It has completed, but there is no active jobs running or services deployed to this particular Kubernetes cluster. So I have a Spark installation in my machine. So it's version 2.4.3. So what I have here is basically a work directory which I've created, and in the work directory I have a data directory and a program that works on this data. So basically this is the program that I'm going to run in Kubernetes. So see what the program has. So pretty simple stuff. It starts the program, it creates a Spark session, and there is 3 tables here: products, sales, and sellers. All the tables are available to us in let me put up the information here. So this is the information that we are reading here. So I have products, sales, and sellers stored as Parquet format that's being read into these tables. And what I'm going to do is simple. I'm going to calculate average, min, and max of all the orders in the sales table. So in sales table, I have one entry for each order. I'm going to calculate the maximum revenue and minimum revenue and average of all revenues that I have. For this purpose, I need to join with the products table, because products table is where I have the price of the product. So in the order table, I just have the number of pieces sold. Yes.
Sorry to interrupt, Mani. Can you just increase the font size?
Oh, okay. Cool. Is this better?
Yeah.
Cool. So so I have this 3 table information, and I'm gonna read them. And there is a join happening. Sales table and products table are going to be joined for this computation. Sellers table is not needed. And notice that we have a simple sleeve, so that we could see the we could see the Spark's driver. The application master can be seen in the UI. So that's the reason the sleep is there for around 2 minutes, 2.5 minutes. So that's about the program. Any questions, or we could?
Yes, Mani, we have a few questions. So first thing is like how we can compare the Spark with the Kafka?
Okay. I think they are solving two different problems. Spark is primarily a computation system. If you have to compute something at a large scale, I have, let's say, an e-commerce website, and I have to compute revenue for each product, let's say, and I have probably 1 billion products sold in the past 6 months. I need to calculate the GST I have to pay for each order, for example. To do these kind of computations at that scale, Spark really helps. Whereas Kafka is more of a queuing solution, where on a real time we get data and we deliver it to consuming nodes. So we don't really process the data there. Or at least it's not built for the purpose of processing the data. It just acts as a broker, message broker, which takes the messages and delivers it to the consumers.
Yeah, thanks, Mani. And the next question is like, so are you using this in POC or production? Because since Skate as a for Spark is not production ready, right? So have you experienced any production use case in your experience, something like that?
Yeah, so Spark on K8s is already used in production by few other companies, but they are taking the calculated risk in terms of okay, I know that the API contract can change anytime, and I know there are the limitations that the system has, and we are gonna live with the limitations for now, because for whatever reasons I prefer to run Spark on Kubernetes, right? So it's not production ready is the guarantee that is not given by the community, but there are always early adapters who want to try this out and take the risk on using these kind of applications on production.
Yes, Mani. So next question is like, is both client and cluster mode, right? Are supported in K8s?
Yeah, so both client and cluster mode are supported by Spark on K8s. The client mode support actually came up pretty recently, but it is supported starting 2.4, Spark 2.4.
Okay. Yeah, that's pretty much. I think so. Let me check one thing. So there is a question. I couldn't get this, but probably let me throw it to you. Would you be sharing the feature parity between Spark on Yarn versus Spark on Kubernetes? Example: dynamic execution, queues, etc.
Yeah. So I think the feature parity is pretty straightforward. I think running Spark on Kubernetes, because it's in the early stages, it's handicapped on few features. So feature parity is just what's missing in Kubernetes. There is nothing unique that we get by running it in Kubernetes as of now, but there are some interesting things that we could have in the future, like using Kubernetes node affinities for scheduling jobs. But at the moment, as things stands now, running Spark on Yarn is a superset for sure. And whatever is missing in running Spark on Kubernetes will be shared.
Yeah, Mani. So one more question, like to schedule this job, right, in Kubernetes. So how does this work? Like, who schedules the job for Spark?
So in Kubernetes, we have to submit the job, and how the whole workflow of what we saw here, right? So this whole workflow, it works when someone is doing a Spark submit. So in this figure, the Spark submit is happening from outside the Kubernetes cluster, but it can happen from inside the Kubernetes cluster as well, from some other pod. Irrespective of that, whenever a Spark submit happens, all these things are spun up only at that moment. So a driver pod is created, then executor pods are created, computation happens, then executor pods are removed. They are done with the execution, once immediately they'll be removed by the Kubernetes. And then the driver pod actually stays, but it doesn't use any resources. It will have just the logs, which we can see. So the moment until before the job is submitted, we don't have these pods running. The moment after the job is submitted, we have these pods running, and we have the driver program creating the executors, and once the execution is complete, executor pods are garbage collected, and we have only the driver pod with resources, the logs.
Okay. So if we are submitting the same job once again, will this driver pod will get reused, or how does it work, Mani?
A new driver pod will be created.
Okay, got it.
So we could see that here in the demo actually. So this was a driver pod that got created when I ran this before. When we submit a job now, we could see another driver pod getting created. Cool.
Cool, Mani. Yeah, got it.
Okay, moving on. So what do we do? Let's do Spark submit. Cool. So let's take a look at this command. So this is the most interesting part here of submitting the job, because I have the master specified as Kubernetes here. Normally, this will be master as Yarn or Mesos, or it will be Spark's standalone master. In this case, it is Kubernetes who is going to be Spark master. So the deploy mode is cluster. We are giving a name, and then we have a bunch of configurations about resources, how much resources driver should take, how much resources executor should take, and stuff like that. And finally comes the file. This is running in PySpark. We could use Spark with Scala or Java as well, but this is a simple Python program. This is going to run in PySpark. And this is basically the file inside the working directory that we saw. So I'm actually, yes, this is very important, because I'm telling Spark which container image to use to run the Spark job. So driver and executor pods has to be created, and based on which image, which Docker image, we have to run the pods. That's what is specified here, and so this is my image name. So because I'm running this in my local machine, I have Minikube, and Minikube has, yeah. So Minikube has some Docker images, and we could see this particular Docker image inside this. This is because I ran one job before. It has already pulled this Docker image. So this is the Docker image which will be used to create the driver and executor pods. If I'm submitting the job for the first time without this particular Docker image, I will be able to see this getting downloaded into this machine, right? So, but how do we build this Docker image is probably one important question to answer. So these Docker images can be built. Okay, these Docker images can be built using this simple tool that comes with Spark. So every time we download Spark, we could notice that there is a Kubernetes folder which is useful. So I'm going to use PySpark. So I'm going to use the Python, and inside this there'll be a directory and Docker file. So this Docker file tells if I have to install Python libraries and all those things into the image, I can do it here, right? So what do I have on top of that? Yeah, so I have the work directory where my information is put in. So this is where my application logic is put in. So in this case, it's a simple Python program. It could also be Scala or whatnot, Java, any program that we could have here. We could put those jars here, and we'll be able to submit jobs to this. So this is basically the structure, but how can we package it? So we have the tool to build Docker images here. So in the bin directory, we could see Spark submit, which we are commonly using. And on top of that, you could also see a shell script for Docker image, for building a Docker image. So, so if I run build, this is gonna start building the Docker image. So this is gonna take some time, so I'm killing it. I've already built the image. So this Docker image, to make it accessible for Minikube, I had to start a local registry, local Docker registry. So that is running in port 5000. So we could see that. So I have this in my local Docker registry. This tells me I have a repository Spark Py, and if I go to the repository, it tells me the tags. I have the latest tag. So this particular local registry is where Kubernetes is going to basically Minikube is going to pull the Docker image from. So this is all for the local setup. If you are using it in an environment, you will most probably be using, if you are in AWS, you will be using ECR for container registry. So you will put your Docker images there, and your Kubernetes cluster will be configured to pull images from that particular ECR, and you'll be able to get the images. So that's a common workflow. In my case, there is a local registry that's running. So this is the registry which is running in port 5000. Cool. Any questions, or we'll proceed?
So just there is a request to repeat when does this driver pod get destroyed, Mani?
Okay, so the driver pod does not get destroyed. The driver pod, once it completes the execution, it gives up all the resources that it was using, and it stays there until we go and manually, reclaim the pod, delete the pod. So that we can see in the demo actually.
And one more question is like, do we need to create two Docker images, one for driver and one for executor?
Yeah, it is supported. We can have two images. Instead of saying container image, we could say Kubernetes driver container image and executor container image. But if you are going to have the same image for driver and executor, we don't have to create two images. The same image will be picked up for both driver and executor, unless we go and specifically say driver and executor.
Okay, that's it regarding question. And one more request is like to increase the font once again.
Further, you mean?
Yeah, yeah. Fine.
Cool. Mm, so without any further delay, let's do a Spark Summit. Yeah, so we could see a driver pod getting created. So in this particular example, executor pods will not be getting created. One, because the problem is very simple, and the other is I'm running this solution in Minikube where only one node, it's a one node Kubernetes cluster. So driver is doing all the computations in this case. So let's see the Spark UI. So Spark master, Spark's application master runs in port 4040. So let's see what's running in this particular. Yeah, so our program computation has completed. It's just see, you can see everything is succeeded. What is pending is the sleep which we have put in so that we can come and browse this UI. So executors, we will not have any executors because it's computed purely in driver. And let's see all the settings that we have done, right? So we have excise, and we could see the Docker image, container image that we specified, and what was the Spark Python file that we specified, what is the driver pod name, the resource request that we made, and yeah, we could see a bunch of such things. And once the computation is over, once the sleep time is over, we could see that this pod will go to completed state. So if we see this, after I have submitted the Spark job, we will have the initial status. Yeah, there is a state change. The new state is running. Yeah, it's in pending, and it has gone to running phase, and the job is still running, and it has completed now. So it would have killed the Spark UI. We will probably be not able to see things here because it's done. And what do we have? Let's see logs for this part. So this pod also completed. This is the pod that was running 939, and that pod is completed now. And let's see what logs do we have in this pod. Yeah, so this is a output. Driver has printed this output. What's the average min and max that we calculated in the program? So this this is where the computation began, and the computation happened, and the results were shown to us. So if we really have a Kubernetes, multi-node Kubernetes cluster, we could even see the executor nodes getting created, uh, and we could see that executor nodes being killed as well. Yeah, so this is broken because the pod has completed. There is nothing to port forward. It's in the completed state. It's not in the running. So that's the live demo. It was a simple Python file in my case. It could be a full-fledged application jar or a full-fledged Python application code. It could be any of these, and it should work the same way. As long as we are able to package it into the Docker image, the simplest thing that we have to do is just ask Spark Submit to use Kubernetes as the master, as opposed to other masters that we use. Any questions?
I think no money. I think we can wait for a couple of seconds. If there is any question, we can address it.
Yeah, okay. I just have one last section to cover. So we talk about the limitations and which use cases this is relevant for. I think this will answer the previous question that we had parked. So primarily the limitations of running Spark on Kubernetes is that it's an experimental feature. Like nothing is guaranteed. The way you submit jobs can change in future in the new release. So you can't count on upgrades will have backward compatibility. That's a primary thing. And the other main thing that any Spark developer would love to use is dynamic allocation, but we don't have dynamic allocation here. So at the beginning of the job itself, the number of executors will be decided, and they will be allocated. There will not be any in the course of the job adding more executors or releasing unused executors. So this means we should already know the size of the cluster, and if we are running the cluster for different use cases of different size. For example, I need 2 executors for doing a particular job, and I need probably 50 executors to do another job. Then we don't have any other option than to have 50 nodes running. So that's a kind of a deal breaker where people are having jobs of different sizes, and where they have not solved for elasticity, where at the end of the job, if they cannot scale down the number of nodes and scale up on need basis, then that will be a big drawback. Again, no job queues and external shuffle service. Currently, shuffle service is implemented as a daemon set. So in Kubernetes world, daemon set means it's a pod that runs every time you add a node to the Kubernetes cluster, or every time every time your node goes away from the Kubernetes cluster, this pod will be removed, and every time a new node gets added to the cluster, this pod will be automatically attached to the node. So shuffle service is implemented in that manner, and currently, because it is sharing the disk with the executor pods, dynamic allocation and shuffle service has to go in hand. So dynamic allocation would need external shuffle service. So these two features will have to be solved together, and they are working on it, and it might be available to us in the coming releases. So there is no job queues available as well. So in the Yarn world, job queues are so famous. It's used for multi-tenancy, where you don't let one tenant eat up all the resources in the cluster and starve the rest of the tenants. So you could have you could solve This partially through rate limiting and quotas in Kubernetes. But what YarnQ does is completely not available here. So then with these limitations, for what use cases do we recommend this? If a customer is already running in the Kubernetes ecosystem, then this is probably a good fit there, because having a Kubernetes up and running is by itself having its own challenges. So just to run Spark, having a Kubernetes cluster running doesn't look like a good option. But if the customer or someone who is trying to use this is already in the Kubernetes ecosystem, then this is a natural fit. We could run it in the ecosystem with these limitations evaluated, of course. So we also have to look at no heavy concurrency between Spark jobs, because if we have multiple Spark jobs running at the same time, you either have to over provision to make sure they all have all the resources, or we will have to work with resource starvation, and each job they will probably not complete as well if they don't get enough resources. Then if we have fixed load jobs, let's say if I have one job which runs at 12 o'clock and it runs for let's say 1 million records, and it's a fixed load. Every day I run for 1 million records, and let's say the job takes 1 hour. Then I have another job running at 4 p.m. which runs for, let's say, 1.5 million records. So if we have fixed load jobs, those kind of use cases are best fit for Spark on Kubernetes as things stands now. For people who have used Spark for a lot of varying use cases with all elasticity factored in, this will probably be a very constraining solution at the moment. Well, that's what we have. If there are any questions, we could talk about.
I think we don't see any questions in chat, Mani. I think it's look good. Yeah, thanks for your valuable inputs, Mani. And I think it's a really very good session, because we were able to understand how the things works internally in Kubernetes to schedule a job and other stuffs. Yeah, for overall, it's a valuable session for us.
Yeah, thanks, Shrikesh, and thanks others for listening. It was a pleasure.
Yeah. So with this next coming and even more hands-on and like internal stuff, how the OS can be built in your hand. So I would like to welcome Ashok for presenting the session. Over to you, Ashok.
Thank you, Srikesh. Hello, everyone. I'm Ashok Gowtham. I work in ThoughtWorks. And a little bit about me. I've been working on multiple technologies, and specifically Java and Ruby tech stacks, and also a bit of Python. So there were some requirements where we ended up exploring options of packaging an application or a set of applications with a custom operating system along with it. So I'll be sharing the experience in that, as well as sharing a walkthrough of how one would go about creating a new operating system itself by putting together packages. Okay, I'll start sharing my screen. Are everyone able to see my screen? Okay. Now, so when would we want to build a custom operating system? That is the first question we should talk about before going into this. Are you looking at customizing the appearance of your operating system that you're using? Then you should be looking at customizing the existing tools and packages installed in the machine rather than looking at creating a new operating system. If you are looking at packaging the changes that you do and make it available for others to try out, then packaging it into a distributable operating system is an option that you could try. And if you are say looking at capturing a market itself newly, like what Android did with mobile phones, then uh, having an understanding of how an operating system works as well as how to put together a new one would help there. So here we are going to look at the high level things as well as the implementation details as well. So I'll begin. So let's understand what constitutes an operating system first. Whenever we say an operating system, the couple of things that comes or examples that come to our minds are Windows operating system, Ubuntu, Mac OS X. So all of these stand distinctly different from each other. And what differentiates each of these? The first thing that would be apparent is how visually they are different. We would have gotten used to the visual appearances of the OS, and if we look at a screen, it will be immediately evident which OS we are looking at. So visual appearance would be the first thing that decides um, OS is different from another OS. And if we drill down a little deeper, there are OS APIs that are available, and that is what we care about as developers. What APIs are available from the operating system itself that we could consume. So those differ between operating systems. In case of Windows, there are the native Win32 APIs that we might have come across. And there are some differences as well between Windows and Linux and OS X, like uh, how the data gets stored, where it gets stored, whether there is something called registry or not. There are many things like those. And tools and applications that are available for use. We would have gotten used to the different tools available in the favorite operating system that we use. In a different operating system, those tools may not exist. So tools play another important part of deciding what an OS is, the identity of the OS itself. And if we drill down even further, then we have the various directory structures that the OSs use. So there are some things that are common across all the variants of Linux operating systems. They all follow pretty much similar directory structures. However, if we compare it to Windows or Mac, there will be starking differences as well. So directory structures also is an important differentiator between operating systems. In fact, all of the above that we looked at are going to be stored as files in the disk. If you look at tools, they are also files that are on the disk that are executed by us. If you look at visual appearances, that are also provided by different assets present in the disk or different applications or packages that provide those. If we look at say the desktop themes, we see variety of themes in each of the OSs that we use, and those themes are coming from different theme files or packages. So effectively, what an operating system is basically defined by the entire contents on the disk. Or if we look at like really flat simply, all the data is getting stored in the hard disk only. So what data gets stored in the hard disk and how it gets stored, in what format it's stored, those are all the things that really make an operating system. So if we can create a similar folder structure and have similar functionalities and make something boot on its own, then we can call it an operating system. And in this talk, we will be looking at creating variants of Linux operating system, specifically under the Debian tree. So where do we start? let's say we decide we want to create an operating system, we decide to make a modification of few packages and include those packages into our OS. And we also want to distribute our OS in a unique way. To cater to all of these, there are some things that are common for any operating system building. We have particularly on the Linux variants. So we would start with creating what is called a rootfs file system dump. So whenever we work on Linux operating systems, we would have come across the file paths starting with the /, and just the / itself is called the root folder. It's going to be the root of all the folder structure that are going to be under it. It forms the base folder under which all the rest of the folders are going to be placed. So a rootfs, or otherwise called root file system, is the basic set of folders and files that together form a Linux operating system. So to create a rootfs file system dump, there are a few options, and Dbootstrap is one of them, which allows us to create a Debian-based rootfs. So it will be making use of packages available from Debian package repositories and building a rootfs. Which packages we start with really makes the difference of which variant of OS we are creating. If we start with a package repository that is available for Red Hat tree, then the OS that we create would be a variant of Red Hat itself. Similarly, here Dbootstrap or Dbootstrap is a tool that allows us to create a rootfs folder structure specifically for the Debian-based operating systems. In fact, Dbootstrap itself, the name itself is created based on Debian Bootstrap. It lets you bootstrap a Debian-based operating system. Although the purpose of Dbootstrap is wide, like you can use it for many things. Here we are only going to be looking at how to use it for creating bootable operating systems. Okay. Moving on. So let's say we have a rootfs file system. Now, can we call it a operating system? We can, but it won't run. We have to make it work by adding a kernel. So kernel is what makes the operating system itself up and running. So whenever we say we are using the operating system, we are actually using the applications or tools that are available in the operating system. And whenever we execute a tool, some other process is loading that application and running it for us. Who starts that application? Who in turn starts its parent application? There needs to be some starting point, and that starting point is going to be the kernel itself. Kernel, once it is loaded and up and running, it will hand control over, or it will load the init process of the operating system itself. Here we differentiate between kernel and an operating system. Kernel is what makes the heart of the OS, so-called OS or operating system, but the rest of the operating system is what defines how the operating system appears and works. So you can make use of the same kernel with different operating systems. And in fact, most of the Linux-based operating systems use the kernel called Linux. And yeah, Linux is a tried and tested kernel that we could use. We would take a kernel package and include it in the Dbootstrap rootfs file system that we are building. Then let's say we do have a rootfs file system which includes the kernel as well. Still, will it run? It won't. What needs to be done to make it run? Somebody has to boot the kernel itself. Somebody has to load the kernel into the RAM and execute it, so to say. So that will be done by what is called a bootloader. A bootloader is the first thing that gets run from a storage like a disk or a CD or a DVD when it is booted. And that bootloader is responsible for loading the kernel into memory and handing control over to the kernel. And the kernel will take over from there. And as I said, it will load the rest of the operating system and hand control over to one of the UI applications or a console-based application to take care of rest of the operating system's session. And there are few bootloaders like Grub. So we will be using Grub here for this session. And Grub is a common bootloader used with most of the Linux-based distributions. And finally, even if we add Grub, what we would end up having is again still a folder structure that contains Grub or the rootfs contents as well as a kernel. But how do we make this a bootable device? We have to somehow make it part of a hard disk, and in a way that whenever the hard disk is booted, the Grub or the bootloader gets invoked, and automatically it takes care of loading the kernel and running it. So we do need to configure both the kernel as well as the bootloader. We have to configure the kernel to load the operating system from the correct location. Then we have to configure the bootloader to load the kernel from the correct location and run it with proper arguments. And we also need to have some configuration to find the bootloader itself properly. And that brings us to the question, who loads the bootloader? So there is yet another system that is there even before bootloader, which is present in any computer that we buy, even if it does not have a hard disk. So that is called BIOS. In olden times, it used to be BIOS, called basic input-output system. That would be the program that is flashed into the motherboard itself when we buy a motherboard, and it would be responsible for making sure any bootable device actually gets detected and the bootloader in that device gets booted. So BIOS was the older days equivalent of what is currently being used, called UEFI. And UEFI is also has the responsibilities of what BIOS used to do, in addition to having way more functionalities and features. And UEFI has support for quite a lot of new modern features like securely booting an operating system, booting the operating system in a very fast manner, and multiple other things. Being able to boot an operating system even without a bootloader, all those are possible using UEFI. But in case of BIOS, it is very primitive and it cannot do many of these that I just mentioned. So we will look at we will discuss a bit about both of these a bit later. So let's look at creating a rootfs. How do we create it? I said we will use Dbootstrap, which is a tool that lets us put together a root file system structure, and that too based on which packages we choose to install. And those packages will be pulled from one of the Debian package repositories. We can configure which repository gets used. Okay. And Dbootstrap also has a couple of features, like it supports what is called a two-stage bootstrapping. The first stage would simply download all the packages that we listed, and it would extract the packages. By packages, I mean the .deb files, which are distributed as installers. In Linux world, there are variety of package managers and variety of package formats. .deb is one of those. .rpm is another one, for example. And Dbootstrap specifically uses Debian package repositories, which means we find .deb packages there. And the first stage would simply download all the packages and extract them into the folder structure, as I said. And any package installer would have a couple of steps. It would contain a collection of files with corresponding folder paths where those files should go. It's more like an archive or just a zip file. In addition to a few scripts that needs to be run when the installation happens. So the installation is, or the package installer would provide a few functionalities to the package itself that is getting installed. It would provide ways to run scripts before or after installation, before and after installation of the package. So those scripts will be run in the operating system when we install a package. But here, since we are still in the process of putting together an operating system, those scripts cannot be run because the operating system itself is not yet cooked. So the packages will be simply downloaded. The scripts will not be run in the packages. Only the folder structure will be extracted and put in a common folder called the rootfs. So once the first stage completes, what we would end up having is simply a folder structure called the rootfs, and it would still have the scripts that needs to be run but not run yet. The second stage of the Dbootstrap is what would run the scripts that are part of the installation packages. And the second stage needs to be run in the same operating system or the architecture that for which we are building the operating system for. So that brings us to a chicken and egg problem. How do we run scripts in an operating system which is not yet built? If the scripts require that operating system to be running, and if those scripts are need to be installed before the operating system can be started, then we simply cannot start anywhere. So what we generally do is find a closest equivalent operating system, use that to load the files, uh, go into an environment where the new operating system's files are available, and only those are available, and within that we run the installation scripts. The installation scripts mainly rely on just the architecture for which it is being run, because there can be different architectures, like Android phones are using ARM based architectures. Windows typically runs on a x86 architecture, and there are also other architectures like PowerPC and Solaris, the old ones. So depending on the architecture, we would have different packages available for installation. So when we download the packages itself, it will be downloaded for the architecture that we chose when we run the Dbootstrap's first stage. So those binaries or the executable files will be able to run only in that architecture. So if we are using, say, a 64-bit machine to create a OS that would run as a 32-bit operating system, then okay, maybe not a good example. Let's say we want to build an operating system using a 32-bit operating system, but the new operating system needs to run as a 64-bit operating system. No, there's no way to run 64-bit executables inside 32-bit operating systems. So what we would have to do is we can run the Dbootstrap's first stage in a 32-bit operating system. We have to somehow create a 64-bit environment, a working environment within which we have to execute the rest of the Dbootstrap stages, the second stage, that is. So if we think about the first time when a 64-bit operating system would have been created, they would have used emulator sort of thing, which would have a working 64-bit processor, and there the installation scripts would have been run. But nowadays, since for all of the architectures we do have some operating system or the other available, we can use any of the operating systems that run on the architecture that we want, and then within that we can run the Dbootstrap second stage. The second stage would run the installation scripts, as I said. And once the second stage is complete, the folder structure that we have would be the representative of a working or a complete operating system itself, including the kernel and the rest of the operating system files and folders. So we need to throw in a kernel to make the operating system function properly. And Linux, as I said, is the name of a kernel. Although it is commonly used as the name of an operating system, it's not the name of any operating system at all. It is name of just the kernel. And GNU was was the first operating system which used Linux as its kernel. When GNU was in development and Linux was in development, when Linux kernel was in a good to use state, GNU was almost ready and available. So uh, they just married these two and created the first operating system that used Linux, which was called Linux plus GNU. And GNU was a collection of tools and software packages which would form the base of the operating system itself, what we see usually as operating system distributions. So nowadays, if we look at, for example, Ubuntu, it should technically be called as Linux plus Ubuntu. Ubuntu is the distribution and Linux is the kernel. So any custom Linux-based or any variant of Linux-based operating systems you see, almost all of them are using the version of Linux kernel that is available as open source. Linux kernel is also taken and modified and used as the kernel in a few operating systems. When Android was released, it used Linux as its kernel in the very initial stages. Later, it was rewritten from ground up uh, with a different set of features. And what we see now as Android is completely a new operating system with a different kernel, which was built from scratch. That said, so bottom line, we just need to include Linux kernel package into our mix of packages when we do a dbootstrap. And this is the package. Linux-image-generic is the name of the package itself, which brings in the Linux kernel. There are also other named packages for Linux kernel. This Linux image generic includes it's a common package which works for or which has packages available for different architectures. So whenever we mention a package name, there could be different versions available for different architectures. The architecture name gets appended to the package name, and then that particular package is downloaded. For example, if you are building an x86 based operating system, even if we mention Linux image generic package, Dbootstrap would automatically find the corresponding package named as linux-image-generic.x86, and that would be used. Okay, coming to the second stage. So in the first stage, the packages were downloaded and just put together in a rootfs. The second stage is where the packages will get actually installed and the scripts are run. Some information about the dbootstrap second stage: it needs to be run in the destination OS architecture, as we have seen already, and it has to be run in a chroot session inside the new OS's root folder. What that means is the dbootstrap command with the second stage argument, when it runs, it should only see the new operating system's files and folders in the same path in which those files need to be present in the OS. If we are developing on another operating system, how do we make sure one of the processes see the files in a different path? That's where a command called chroot comes in. It means change root. What it does is it takes a subtree of folders starting from a particular root folder. It could be any folder, and it runs a given application or a command inside inside an environment which can only see the files and folders present under the root folder that we chose. For example, we could create a folder in our in our home directory. Within our home directory, let's say we create a folder called working directory, and within the working directory we do the dbootstrap first stage. That would put all the files in that working directory. Once done, we can simply say chroot space the path to the working directory. That would create a chroot environment within which by default the shell command would be run. It would be /bin/sh that gets run, and any tools or commands that you run inside that environment will always only see the files and folders that are present in that operating system, or files and folders present in that working directory that I said. Okay, let's look at some code now. I hope the font size is good enough. Yeah. So we'll start here. Let's say to start with, we would list down all the packages that we would want to install as part of our operating system. For example, let's say these are the set of packages we have chosen. Some of this are mandatory. You can say up till here. All of these are mandatory based on the choices that we made. We have Grub related packages, and we have few file system related packages that will be used for creating the partitions and all. And we have the Linux image generic kernel package also. Util Linux is the package that brings in most of the common utilities that we find in any Linux operating system. And init is one package that brings in the init process, which the kernel hands control over to right after the kernel is loaded. And it is the responsibility of the init process to make the OS function or load the rest of the operating system and make it function as intended. And I just added a couple more packages here, like for example, Python and NCDU. NCDU is a utility that gives a console-based UI for browsing the files as well as analyzing where the disk usage is going. Okay. So let me run these. To start with, let's assume I am in a operating system, or I am in a Ubuntu machine, and let's look at this one. So it's a Ubuntu based machine that I'm using right now, and I source a few functions to make it easy for this demo. And we start with listing down the packages that we want to install. I'm just assigning this to a variable called packages to include. Then we create a folder called work under temp and then cd into that folder. For now, this is an empty folder. And this folder is going to become the root fs folder itself once we have done the bootstrap. Now, to actually download the packages that form the OS, we run the dbootstrap command. And this is going to consume some time because it's going to actually download the packages. It will take a long time to complete. So all the packages that we have listed here, those packages will be resolved, and their dependencies will be fetched, and all the dependencies will be resolved, and finally a larger list of packages will be downloaded and installed. So Here we can see the output from Dbootstrap itself. It's trying to resolve the dependencies of packages. So let it happen. So once the Dbootstrap command completes, we would have a rootfs folder structure. Which point all the downloads would have happened. Then we no longer need the internet to proceed. So just to take a look at the Dbootstrap command itself, it takes a few arguments. So here we mention the package repository that needs to be used. Typically we could use archive.ubuntu.com/ubuntu, or I'm using one of the mirrors that is closer to us so that the downloads happen faster. And we also mentioned the list of packages that we listed above so that Dbootstrap gets to choose those packages alone. And we also specify the variant of Ubuntu itself. Like there are multiple sets of repositories under this package URL. So we specify which repository or distribution to use. And we also specify the architecture that we are targeting. Here I'm specifying AMD 64, which means it's a 64-bit operating system that we are trying to build. And there is a variant option to Dbootstrap, which has a couple of values available. Build D is the one that we need to use if we are trying to build an operating system that needs to be booted as an operating system. Dbootstrap can also be used to put together the rootfs alone. The rootfs can be used for several other use cases. If you say have a broken system where a few files are missing, you can create an equivalent rootfs using this Dbootstrap command and copy over the files from that rootfs to fix the system. So for that, we don't need to give build. We can simply give another option. There are also options for chroot based, or there is an option called a chroot variant, which will allow us to simply use that rootfs just for doing chroot. If we wanted to use the operating system just in a chroot environment, not planning to boot it as operating system, then we can simply give chroot here. And finally we have the option called foreign. If we don't give foreign, both the two stages of Dbootstrap will be run one after the other. If we give foreign, just the first stage will be run in the current operating system that we are using. Later, the second stage can be run in a different machine or architecture. And the second stage needs to run in the architecture we have specified here. Once all of this is done, we would have a rootfs and of the first stage alone. Then there are a couple more things that we need to do. Add in a folder called /proc. So /proc is a folder in Linux OSs that provide information about the running processes. And it is a folder that gets mounted from a kernel device. It's not a real folder structure that exists in the system. It's just a empty folder that will be used to mount another file system called the procfs, which will provide information about the running processes. Then the next thing is once we have all of this ready, we can have two options. One, either chroot into the operating system and try the different tools inside, or we can make it boot as a proper operating system itself. So here we can see the first stage has completed. Now doing ls, we can see the typical root folder contents of any Linux operating system is present in the current working folder. So as we said, this is called the rootfs itself. Now within these folders, we would find the rest of the folder structure we would find in any given Linux operating system. the things that we have to look at are, there is another folder called Dbootstrap, which is usually not present. So this folder will contain the Dbootstrap command itself, which needs to be run with second stage argument. So to run that, it is available here. Once we run the second stage, it will automatically install all the other packages and clean up itself. So we can take a look at a few things like /bin. So we see many of the tools available here: rm direct, dir, mv command, mount, more, ls. All of these are now installed, and most of these commands came from the package called Linux. Sorry, what is it? Util Linux. Okay. So now we can use chroot and give the current folder, and this will give us a prompt. We can see here, and this prompt, within this prompt, if we do if we run commands, we can see that we are in the root folder right now, and the contents of the root folder are the same contents that we saw in the working folder. So basically now, right now we are in an environment where the root folder itself is the original folder where we did the dbootstrap stage 1. So these files are here, and if we run say /bin/bash, it would be available here. It is not running the bash shell from the outside operating system where we did the dbootstrap command, but it is trying to run bash command from inside the rootfs. Although who loads the application and run is simply the host machine's kernel, the same kernel in which we were running the dbootstrap commands. We don't have, we are still not booting the new kernel that we downloaded. Okay. Bin bash won't work right now because there are many things that are not set up properly yet. To start with, the user itself is not created in that operating system, so it won't be able to log in with the new shell. So we are back in the previous environment where we were. I wanted to just show the files that get created here. So once we have this, we would be able to run the next stage of dbootstrap. So for running the next stage, we need to do a couple more things. We need to create a new, first of all, we have to think about where our OS is going to boot from. We started with, say, Ubuntu operating system where I downloaded the files. That operating system is not something that we would want to rely on for running our operating system. It should not have, our operating system should not have a dependency on that Ubuntu machine where we are developing it. Ideally, we should be able to say take a brand new hard disk and be able to flash our operating system into that one and make that disk bootable. So to start doing that, we need to think about what needs to be done to a brand new hard disk. So ignore the few things that you see around here. Yeah. So okay, there are a few more folders other than proc folder that I mentioned that needs to be created. /dev and /sys. Some of it we might have already noticed, it is already there, so we didn't have to create it. If we do a chroot and within that, if we run any command, it could mount a real devfs in the dev or procfs in the proc. That needs to be unmounted if at all we do anything within the chrooted environment. So the next thing that we have to do is set up partitions. So to create partitions, we use a command called fdisk. Fdisk is capable of creating partitions in a disk, and also go back. So let's talk about disk versus partition. We might have interchangeably used partition versus disk, but partition is the subdivisions of a disk itself. If we take a physical hard disk, the entire thing is called a hard disk. We can have multiple partitions made inside the disk. And in Linux file systems, in Linux operating systems, we might have noticed these kind of files /dev/sda1 or /dev/sda. What this represents is a partition. If we see SDA1, that represents a partition. If we see SDA, that represents the entire hard disk itself. And if we see SDA versus SDB, those two are two separate hard disks. So this example that we are seeing with 4 devices is basically that machine contains 2 hard disks. One is named as SDA, and the first hard disk has 1 partition. The second hard disk, which is named as SDB, has 3 partitions. And each of this partition needs to be formatted with the file system before we can start using the partition. In Windows, generally we would have come across um, FAT32 partition or NTFS partition. In Linux, typically ext based partitions are used, or file systems are used. So FAT32, NTFS, ext3, ext4 are all different file systems, and each partition needs to be formatted with the file system. So we have already talked about UEFI versus BIOS. So there are few specific things that we have to do additionally for UEFI based or OSs that needs to support UEFI based systems. Those are we have to have 2 partitions mandatorily. One has to be a FAT32 partition. It could be a pretty small partition, like a few hundreds of MBs, and that partition will contain the bootloader and maybe even the kernel, and the bootloader will have to mount the other file system or other partition, and then load the kernel and execute it in case of UEFI. In case of BIOS based systems, there can be just a single partition with the entire operating system and bootloader sitting in it. BIOS will simply hand control over to the first sector of the first partition in the hard disk. And it is the duty of a bootloader sitting in the first sector to take control from there and load everything else. In case of UEFI, it is a bit mature. It can understand file systems. It can understand folder structures. So there is no requirement about specific sector that needs to be used. So to keep disks compatible with both UEFI and BIOS based systems, the first partition is typically left for BIOS's use. We can have a bootloader present in the first sector so that the disk is bootable as a BIOS in a BIOS based system, while still being able to boot the same disk under a UEFI based system also. So UEFI does not have any dependency on the first sector. It simply loads its files from a specific path in the FAT32 partition that it finds. It will look for dot UEFI files present in all the storage available, like different partitions under different disks, and wherever it finds a matching file, it will try to load that file and execute it. And if the file executes, it will be listing that file, that particular path or partition as a separate operating system. So with UEFI based systems, we can even have multiple operating systems getting detected by UEFI without having to set up a bootloader that supports all of these OSs. All right. So how does the operating system really boot? As I said, the BIOS hands control over to the bootloader, and then bootloader hands control over to the kernel, and kernel loads the operating system and continues to run, forming the base of the operating system itself, in base of the running operating system. So we have taken a look at what constitutes an operating system. We have seen how to get a kernel, and we have also added the packages to get the Grub bootloader. And we also talked about BIOS and UFI. Now to put all of these together, we need to bind them all together with a disk format and a partition. So let's look at this. So here we look at fdisk command that we can run, and fdisk is an interactive tool, so it will be printing a lot of output and asking us to choose values. We would be entering individual characters or numbers to choose different options. So here it is just scripted out here. So we just list the partitions and create a new GPT based partition table. We did not talk about partition tables. So when we say we create multiple partitions in a hard disk, somewhere the information about partitions itself needs to be stored, and that information cannot be sitting inside a partition itself. So there needs to be something present in the disk itself before we start defining partitions. Some space present at a disk level that will be used for representing the meta information about what partitions are there. So typically for that, the disk will be formatted with a partition table, and then we would start creating partitions. So the first partition is typically not the will not be using the initial few sectors of a disk. The initial few sectors will be used by the partition table, and the partition table will have information about the first partition, for example, and BIOS would be using the first partitions first sector to load the bootloader from. Okay, so there are MBR partition table, master boot record, which is the older style of partition table, which has limitations on how many partitions we can create. It has just a 2-bit identifier for the partition ID, which means there can only be 4 different partitions that can be created under a MBR based disk. And it was not pretty, or it was very recently, in the last decade, where new partition tables were started to come, and very recently we can see systems available off the shelf that use GPT based partition table. GPT stands for Grand Partition. Sorry, okay, forget that. I missed that. So GPT allows creating partitions with larger capacity, as well as it allows creating way more number of partitions, like up to 128 partitions, I think, in a given disk. And it supports disks of even petabytes in size. MBR has limitations on maximum size of a partition as well as maximum size of the disk itself. It cannot work with disks greater than 2 TB. GPT can easily work with even larger capacities. So we choose a GPT partitioning table because we want to use a modern option, and we create a partition. We just choose the default number, the first partition, and specify a size for the first partition. And this number is simply based on how much size that we want to allocate for the first partition. And in case of UFI support, we need to have we need to leave the first few sectors, as I said, for compatibility with BIOS. So that means we just start our first partition at 1 MB address, so that the first 1 MB of storage will be not used at all. If at all needed, BIOS can make use of it. We can, if we want, support BIOS compatibility as well by simply putting a bootloader in the first sector. Then we create this first partition for 200 MB size, plus 200 adds 200 more MBs, and rest of the disk we create as yet another partition. And this partition we create as ESP. The first partition, the 200 MB partition, we create as type ESP. It means FE system partition. That will be the one that will be looked for by UEFI when it searches for available bootloaders to boot from. Then we create the rest of the available disk as another partition here. We could choose to do other things as well, but for now we simply take the rest of the entire thing. Then wipefs will destroy any existing file systems, if any, not needed for a brand new hard disk. But in case we had been playing around with the commands, there might be an existing file system that is already there that might cause an issue. So we simply make sure we erase the file system related meta information in both the partitions. Then we partition the first partition, we format the first partition with FAT32 and format the second partition with say ext3. Then we can simply start mounting the partition as a folder. So this is where things become interesting. So far we were talking about a raw hard disk. Now we have partitions, and the partition can be mounted in a particular folder. And once the folder has been mounted, we can start writing contents into it. And the content that we are going to write is our rootfs that we had earlier. So once the partition is set up, we would ignore the contents here. So okay, at this point, assume the rootfs has been copied over to the new partition that we just mounted. So at that point, the new hard disk is now set up with the partition, and also the contents of the rootfs that we put together using Dbootstrap. Now is when we have to configure the operating system to be able to boot properly. So when we look at Linux operating systems, it needs to have ways to install additional tools for installers to work, like apt or any other installer. The sources or the repositories where the installer looks for needs to be configured. So that's what we do here. And we run the Dbootstrap's second stage at this moment. And that needs to be run inside a ch rooted environment. So here we do a ch root and give the root folder, which is the temp/working directory. Then we execute /bin/bash inside that environment, and then run these commands inside the ch rooted environment. So Dbootstrap, a second stage here, would do the things that we talked about earlier and give us a operating system folder structure with all the things set up. And it is after this point, it is equivalent to a machine that has been turned off. It has everything in place how it needs to be. We just need to add a few more things, like configuring the fs tab. So fs tab is a file present in etc folder, which we can edit to make sure which partitions get mounted when the OS boots. So we have two partitions so far. One is the ESP partition that will be used by UFI, UEFI, and we have another partition where we install the rootfs. So we mount the rootfs as the root folder itself in the destination OS, and we also make the FE files available for editing inside the operating system under this folder. It could be anything, we just choose to have it like this. It need not even, the FE partition, sorry, ESP partition need not even be mounted, but here we just choose to mount it. Then the higher level parts, like we have to configure the network so that it is available here. Here the assumption is, let's say we have a Ethernet card present in, or NIC card present in the machine, so that we can configure it like this. This will like configure the network to work with the basic settings. We just assume DHCP is available in the network. The IP will be automatically assigned and so on. And we just assume that we have one Ethernet device available under the name ETH0, which is the default byte usually. Then we need to have the host name configured for the operating system. Usually when you install operating systems using a UI installer, there will be text box asking for machine name or server name, and that basically gets put into this file. We just do the same thing here. Once all this is done, here we are going to install the bootloader itself and configure it. This is like the last step that we need to do to make the operating system and kernel boot properly. To install the bootloader, which is Grub, there is a command available which gets run inside the operating system, which will do the installation of Grub bootloader itself. And the installer is called, Grub installer is called Grub Install. And this is available in a separate package that needs to be installed, which we have chosen in the Dbootstrap's first stage package list. So here we have grub2. This will provide the executable called grub install, which will in turn install the grub bootloader into the right location in the disk. So that also needs to be run inside the chrooted environment. And this grub install will automatically look for where the operating system, where the kernel is, and the disk UUID, the disk identifier, and include that in its configuration by default. If we want, we can go and modify the configuration also. That's precisely what we are doing here. So that things will be under our control. We can choose what we want to do here. So this is how we configure the grubs. This is the grubs configuration file, and we create a menu entry called custom Linux, and these two are the required commands in the grub bootloader. One specifies to load the Linux kernel from a particular path, giving the parameters to the kernel itself, and initrd is the one that loads the disk image. This is a disk image that the kernel will be seeing when it is loading. It's not the same file system that we created. It is a temporary environment within which the kernel would be doing things before it is going to load the operating system. So once we have configured Grub, we should be able to boot the operating system itself. The last thing, really last thing that's pending is only to make sure we are able to log in into the operating system. For that, we need to have a user, and the root user is a user that automatically gets created. We just need to set a password so that we are able to log in. And we set root, for example, here. So that we will be able to log in and start using the operating system. So once we have done all this, the hard disk that I talked about is now having all the things required for the operating system to boot and function. So this hard disk can be used to use the operating system, but we don't have an installer to install the operating system itself. So installer is a different game altogether. When we say we have created an operating system, what we have really created is the disk image of the operating system that can be directly booted into when it is there on a disk. So let's say we had a new hard disk and we did all this. Now this new hard disk is bootable. And if we boot into that hard disk, we are able to see the new operating system that we just created. However, if you wanted to be able to distribute this operating system to others for them to be able to try, you would choose to distribute it as a ISO file. So ISO files can be burned to a DVD or a pen drive, and using that we can install an OS into the existing hard disk. So the installing the OS part is what we are looking at right now, this file. So for whatever we have talked about, running the stage 2 of Dbootstrap and setting up different things, these are all part of the installation of the OS stage. But there needs to be somebody or some environment where we run these commands. That is the installer itself. That again needs to boot from a USB pen drive or a DVD disk. And DVD disk or a USB pen drive is again just yet another storage. So that storage needs to be bootable, and that needs to have an operating system to boot, and that that storage medium would have the same requirements that we went through so far for creating a new operating system. So effectively, whenever we say we download Ubuntu ISO and burn it to a DVD, now what we have is a Ubuntu installation disk. That disk actually contains two operating systems. One that boots when the DVD is inserted into the machine and loaded. A first operating system gets booted, a very stripped down simple one, which in turn provides a user interface for us to install the actual operating system. So that is the other operating system that is sitting inside the DVD, which is still just an archive, which gets extracted, and then the rest of the commands that we looked at are run. So once the installation completes, what we would end up having is the actual operating system on the hard disk. Okay, so I'll show. So we have a script also which created an operating system ISO file, and just to save time, already ran it, and this is the output, for example. So here is where we run the Dbootstrap first stage, which generates the rootfs of the actual operating system. Then we create the we package the rootfs itself into an archive so that it can be distributed and then later installed into another machine. So what we would end up creating is called a squashfs file. Squashfs is again a file system, a compressed file system, which is a file system that can be used on a single file. You can have a file with squashfs format, and it can hold an entire disk's worth of content. Meaning it can even store lower level information about the metadata of partitions and all inside the file. If we use a zip or rar or tar file, it cannot represent the meta information about disks and partition tables. Squashfs can represent that. So we create that, and finally we create the ISO file itself, and let's try booting this ISO. So I just create a new virtual machine. And choose the new image that we just created. And we start the virtual machine. So what we see here is the bootloader's input screen. This is the bootloader of the ISO image itself. So as I said, there are two operating systems itself. One is the actual operating system that we want to install. The other one is a stub just to boot this um, what do we call the optical disk or the installer itself, and within that we will be able to run the actual OS. So what we see here is a operating system booted and ready, and this one is the installer OS itself. Typically this would have a user interface that asks for different details. Instead we have where are we now? Go to slash. Here we can see custom Linux. I go into custom Linux. So this is like a installer archive that I have created that would have a shell script along with it, which will do the installation. So some of the things that we usually enter while uh, running a operating system installer are these, where to install and other options. I just give the default ones and continue. Okay, there's something wrong. Just as usual, whenever we do a demo, something fails. So if we look at the list of packages we have put together, we did not have any package that brings in a graphical user interface. We did not have X11 server or Wayland. Those are the ones that provide the desktop manager itself. So because of that, what we end up having is a console-based Linux or a server type Linux OS. Okay, this time it's going through. So here we are formatting and partitioning the disk and then running the Dbootstrap's second stage. Once it completes, we would have the new operating system installed into the hard disk of this new virtual machine. So this again is going to take some time because it's going to install and verify the list of all packages that we included, and maybe we can take some time to answer any questions anybody has.
There are no questions at Ashok.
Okay. So to custom, so far what we saw was building an operating system. When we say custom operating system, there needs to be something different about this operating system, right? So typically what people customize when they mention about new operating system is start with looks and feel of the operating system, and maybe add in a custom application of their own into the operating system. Uh, Even the install, if you download a operating system and install, it would contain that particular vendor's um, software already part of it. So if we know how to create a operating system installation, then we can just add in the packages that we build into the mix, and whenever somebody installs this operating system, they would already have the package as part of the operating system itself. And typically, the visual appearances are customizations on existing tools. It Not many people nowadays go and write everything from scratch. We always build on top of what is available. So Genome is a popular software package that provides the desktop shell itself. What we see as a desktop environment itself is provided by uh, Genome suite of packages. So we would take Genome, start customizing it, make modifications, package the changes along with the Genome, and include it in the custom operating system that we are building. And then that would um, that operating system, if somebody installs, they would start seeing the new customized things. So of course, building a OS is an elaborate one, so it cannot be covered within a single session. If there are any questions, feel free to share with us. And also, if there are any requests to go into more details of whatever we have touched upon so far, we can do that in consequent sessions as well. Stay in touch with us and let us know if you have any questions.
Sure, Ashok. I think I was just closely monitoring the chat, but there was no questions. But actually, we felt that there was a clear explanation for each and every step, and we were able to understand the flow, how the OS can be built within some time, and also like how the internal flow works. And yeah, it was a purely a good session overall. And Ashok, do you have anything to present?
Um, that's all I got. Just wanted to show a demo and then facing some issues. All right, that's all I had. Um, so that there's nothing fancy that I could showcase either, even if it booted properly. It's just a console-based Linux operating system that we put together so far, and yeah. So the scripts that we saw here, I can share the details maybe in a separate time. That's all I had. Thank you, everyone.
Thank you, Ashok. Yeah, thank you very much for your valuable inputs. And so thanks all for joining the Geek Night, 44th edition of Geek Night this time. And if you need any more, like if, as maybe Ashok mentioned, if some more topics need to be covered in depth, please post us in the feedback form which we share. And so you can see the feedback link in chat, as well as I have sent it an email for all RSVP members. So please do feedback. it will be a valuable input for us to improve further. Yeah, thank you. Good night.